Good morning, everyone. Hope that you guys are having a good start to your Thursday. I hope that everyone took the opportunity to watch the pre-recorded lecture from yesterday. That lecture covered two important topics that we're going to be revisiting today. So let me do one thing. Let's go. Those important topics are none other than balancing chemical reactions, and the mole. Now, there's a lot to unpack with both of these, and we're going to kind of get into both of them today with our discussion of stoichiometry. Now, one reminder, you have a quiz due tonight at 11:59 p.m. Then you'll have another quiz due quiz opens at 11 a.m. and closes at 11:59 p.m. on Saturday. Opens at 11 a.m. Friday, Saturday. So make sure that you do both of these. Um, so when it comes to balancing chemical reactions and moles, basically what you want to do is you want to follow some of the important parts about um, the laws of conservation of mass. And if you follow that, you're going to be in pretty good shape. Essentially, what you want to do is you want to make sure that the number of atoms are equal on reactants, reactants, and product side. Um, so if you do that, you're going to be in pretty darn good shape. Now, could anyone tell me if like half of their screen is obscured right now? Or can you see the word stoichiometry clearly on the video? Add a one to the chat if you can see it. The number one. Okay, good. I'm trying just a different way of looking at the setup. Okay, thank you. So, stoichiometry. Stoichiometry brings into play both balancing reactions and the mole. Now, balancing a chemical reaction, what you need to know is you've got to get everything on, on the same. Sorry, let me rephrase that. When it comes to balancing chemical reactions, what you have the power to do is modify the coefficients. This right here, this number two indicates that you have two carbons. Okay. Well, this two right here indicates that you have two oxygens. The difference is that when you see a subscript says number of atoms, and I'll say number and type or identity of atoms in a molecule. Now, what that means also is this right here, this two right here indicates that we have a carbon and a carbon that are separate things. There is no bond between these. So nothing connecting these two carbons. So they are floating around freely. Now, O2 by comparison. So this right here is represented by our two Kit Kats. These two Kit Kats are in contact with one another. So those two things make up this whole molecule. Now, Over here on the product side, our 2 here indicates that, well, there's one CO and then another CO. When these two atoms are written next to one another without any sort of space between them, that indicates that we've got these two atoms that come together to make one molecule. So whenever it comes to balancing a chemical reaction, you are more than able to change the coefficients, but you cannot change the subscripts. The reason that you cannot change these subscripts right here is because then you're changing the molecule. So if you saw this same sort of thing and you saw an unbalanced equation, C plus O2 yields CO2 and said, or sorry, saw this and said, oh, well, I know how to balance it. I'm gonna balance it like this. I'm gonna throw a 2 down here. Balanced. Nope. The problem with that is CO and CO2, they're different. They are different molecules. This one right here, we exhale carbon dioxide. You exhale that, and that's arguably a good thing because plants need this. I'm gonna do plants, smiley face. Does anyone know anything about CO? Could you add to the chat what CO does? Or anything that you know about CO? Oh, okay. Um, in terms of inhaling CO, good or bad? Yeah, it's very bad for you. It's potentially fatal. Um, CO2, yeah, it's potentially fatal, but the quantities of carbon monoxide versus carbon dioxide that lead to a fatality are much different. Okay, now when we see something like this, when this equation is balanced, let's see. Okay, so we've got this and this making this thing right here. Well, if you got 2 of these, or sorry, when the coefficients are just ones, this is not balanced because there's 2 nitrogens, 2 hydrogens. Now there's 1 nitrogen and 3 hydrogens. If we upped this to 2, well, then our nitrogens would be balanced. We're good there. So nitrogen's balanced. We've got 2 on each side. What about our hydrogens? Not quite. What number could we put in front of the H2 to make this a balanced chemical reaction? Add it to the chat. So I'll draw out effectively what I've got on the right-hand side. I've got, there's my other NH3. Okay, so I've got 2 NH3s. So blue, 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 blue. Sorry, my color scheme's a little bit off. How many H's do I have on the product side? Add to the chat the number of hydrogens that I have right now on my product side of my reaction. I've got 6. Okay. How many H2s do I have on my reactant side? Add that to the chat. 2. Okay. Um, now how many hydrogens do I have on my product side? 4. Okay. So right now, what is my coefficient? 2. Okay, so what coefficient would I need to have to get an equal number of hydrogens on the reactants and product side? What coefficient should I use? DDA, perfect, 3. If I put a 3 here, then I've got this. 6 hydrogens. Wonderful. Okay, so that's what we want to be able to do. We want to be able to balance this. Now, balancing this relates to moles. If I have 1 mole of pencils, I have 6.02 times 10 to the 23rd pencils. That's a lot of pencils. Um, if I have 1 mole of carbon atoms, add to the chat the number of carbon atoms I have. Perfect. 6.02 times 10 to the 23rd. Great job. Now, I'm going to ask you this question. Okay, so these statements right here are highlighting that point. I have 1 mole. How many atoms do I have? Okay, so that's drawing this connection. Now, my next question is, if I had 1 mole of pencils, and I'm talking just the number 2 pencil, could I pick that up? And I am strong, but am I strong enough for that? And if you need to, write out the whole number. DDA, you're absolutely right. No, I could not. I could not lift that. That would be impossible. Now, that's because I can't even fathom how heavy that is. Let me ask you this. If I had 6.02 or if I had 1 mole of carbon atoms, could I pick that up? Absolutely. Um, and if I'm looking at this and I'm like, well, how can how much does that weigh? Well, I'd look at the periodic table and I'd see it's approximately 12 grams. So if 1 pound, if 1 pound is 454 grams, you're absolutely right. That's their atomic weight. If 1 pound is 454 grams, tell me this, yes or no, do you think that I can lift 10 moles of carbon atoms? Yeah, because answer in the chat, what is the mass of 10 moles of carbon atoms? That's right, 120, because 10 moles, C atoms. What I need to do is I need to go back to my definition. 1 mole of carbon atoms is 12 grams. So 10 moles of carbon atoms is 10 times 12 or 120 grams. Now, I want to put this in a different set of terms. Do you think that I could lift 1 pound of carbon atoms? Yes or no? Absolutely. Now, approximately how many moles of carbon atoms are in 1 pound of carbon atoms? And if you want, just plug into the chat the math that you would do to solve that question. Sparrow, I think that's about right, just about right. I'm guessing that you did the math. Yeah, 454 divided by 12. So almost 40 moles of carbon atoms. I could lift that. Okay. Um, I couldn't even lift 1 mole of pencils. So that brings us all of this math right here is this right here. This conversion, moles to mass. Now, if you can go from here to here, then you can go from here to here. And ultimately, you could go from this point right here to this point right here. You have this intermediary that you go through. Okay. Now, when we're converting masses of something, we always have to use the periodic table. That's our reference point. I know some of these numbers. So what I'm going to do is I'm going to tell you this, and I want you guys to use your calculators and put this together in the chat. What is the molar mass of sugar? Now, I'll tell you that carbon has a mass of 12 grams per mole. Hydrogen is 1 gram per mole. And oxygen is 16 grams per mole. Use those numbers and tell me what is the mass of 1 mole of sugar. And I'll do the same thing. 342. I think that sounds about right. 16 times 11. That gets me 176. Plus 144 is 12 times 12 plus 22. Yeah, 342. Great job. So ultimately, that adds up to 342. Now, 1 pound of sugar is going to be, how many grams is 1 pound of sugar? Thinking back to this, how many grams is 1 pound of sugar? Well, 1 pound of sugar is going to be 454 grams of sugar. Because if I have 1 pound of Doritos, what's the mass of 1 pound of Doritos? 454. That's a definition. It's kind of like a mole. If I had 1 mole of Doritos, I'd have 6.02 times 10 to the 23rd Doritos. Now let me ask you this. Just thinking about all these different numbers and these different terms, let's imagine that I had 1 pound of sugar. Do I have more than a mole? Less than? Or exactly 1 mole? Didier, why do you say more than? 1 pound of sugar. Done. You're exactly right. If I had 1 pound of sugar, that means I have 454 grams of sugar. 1 mole of sugar is 342 grams. If I had 1 pound of sugar, I've got 454 grams of sugar. 454 is more than 342. Absolutely right. Now, looking at these two questions, or at these two examples, we got a Twix bar or Skittles. They have 25 grams of sugar and 45 grams of sugar, respectively. Your body kind of doesn't care about the masses. It cares about the number of moles. Chemical reactions relate to and care about numbers of moles. So your body is like, your body catalyzes chemical reactions. And so all of the enzymes that your body uses, what it's going to do is it's going to say, okay, well, I need to convert 25 grams and 45 grams into moles. I need to convert this into number of moles. Now, in both of these cases, you have less than 1 mole because 1 mole sugar is 342 grams. Which one of these has the larger number of moles of sugar? The Skittles do, no doubt about that. But at the end of the day, your body needs to know about how many moles this has. because ultimately that's what matters for all of your different systems within your body and producing hormones and metabolizing sugars. Now, this is a good slide to show relationships. 1 mole of carbon atoms is 6.02 times 10 to the 23rd carbon atoms, which is 12 grams of carbon. 1 mole of oxygen atoms is 6.02 times 10 to the 23rd oxygen atoms. We know the 1 mole of sugar because we defined it a little bit ago. This right here. So we use this information on this slide right here. This is not a number I expect you to memorize. I expect you to, however, be able to calculate what is the mole or what is the number of moles here based on the mass or based on, here's the formula. What is the mass? Okay. Now, what this demonstrates right here is we've got these different quantities defined. 12 grams of carbon, 32 grams of oxygen is 44 grams of carbon dioxide. Now, what's conserved here? Okay, well, let's see. Is our mass conserved? Well, 12 grams and 32 grams come together to make 44 grams. So our mass is conserved. Okay, then what about our atoms? Okay, so when we have this balanced chemical reaction that looks like this and this, we've got, well, the number of carbons are equal. And, oh, sorry, never mind. We didn't have to do that. The number of carbons are equal. The number of oxygens are equal to one another. Yeah, we conserve the number of atoms. Molecules. This is a molecule. This is a molecule. So we reacted 2 molecules to make 1 molecule. Are our molecules conserved? No, they are not. Okay, there we go. But that's fine. What about the number of moles? Well, on the reactant side, we had 1 mole of this react with 1 mole of this, and we made 1 mole of this. If our number of moles were conserved, we would go from 1 mole and 1 mole as reactants to make, well, we would have 2 moles as reactants make 2 moles as products, but we do not do that. Now, here is a balanced chemical reaction. C3H8O2 reacts with CO to produce CO2 and H2O. Now let's count up everything on each side. All of our atoms are carbon, hydrogen, oxygen. CHO. How many carbons are on the reactant side? Tell me that number in the chat. 3. Now tell me how many carbons are on the product side of the reaction. There are 3 carbons because this coefficient applies to this whole thing, but this 2 only corresponds to the oxygen. So CO2, carbon dioxide. We've got 3 carbon dioxide, so we have 3 carbons. Now, how many hydrogens do we have on the reactant side? Yeah, we've got 8 hydrogens. And then how many on the product side? Great. Last but not least, how many oxygens do we have on the product side? I switched it. I went with products instead of reactants first. Does that matter in a balanced chemical reaction? No, it doesn't. I've got 10 reactant oxygens and 10 product oxygens. Answer me yes or no in the chat. Would my Would your responses be different if there was not a 3 here? Okay, follow up to that. If I didn't have that 3 there, would this chemical reaction be balanced? No, it wouldn't. Okay, so what if I were to, this is kind of balanced, or this is balanced. Does it add a yes or a no in the chat if you agree that this chemical reaction is balanced? We got the same number of carbons, hydrogens, and oxygens on each side. Okay. Now, this is this is a nice ratio. I need one C3H8 to react with 5 O2. And whenever I do that, whenever I have one C3H8 and 5 O2, how many CO2 do I get? Add it to the chat. Okay. How many H2O do I get? Great. Okay. Now, what if I had one C3H8 and one O2? Let me ask you this. Would the reaction take place at all? Add a Y or an N to the chat. What if I told you that it did? This is a ratio, 1 to 5. Um, but if instead of 5, let's say that I only had one O2, the product would have to change. Okay. If I had one O2 and one C3H8, actually, I'll come back to that in just a second. Let's say hypothetically that I roll up and I give you one C3H8 and 5O2, and you make 3 CO2 and 4 H2O. Is that what's going to happen? Y or N to the chat? Yeah. Okay. Now, you've taken my C3H8 and my O2, those exact numbers, 1 and 5, and you've made this and this. Do I have any more C3H8 or O2 left over? No, because they've been completely consumed. Do you follow that? Add a Y or an N to the chat. So a visual of this looks like this. Here's C3H8. I think that it's helpful to draw the molecule when you can, or have the molecule, a visual of that molecule. Add a Y or an N to the chat if you'll agree that this that I've just drawn is a good structure for C3H8. And confirm that you're good with that. Okay, now I'm going to draw O2. And these are rough drawings of O2. But add to the chat, how many O2s have I drawn? Okay. So if I've got one C3H8, 5 O2s, and then I make one CO2, how many O2s do I have left over after I've made this? Because I had to use the O2. Okay. Does everyone follow that? Okay, so I'm going to scribble that out. Does everyone agree that what I see on the left-hand side reflects the numbers and the products on my right-hand side? Okay. So let's go ahead and do all three of my CO2s. Does everyone agree that this is three CO2s? Wire into the chat. And those are some of my products. Okay. So tell me how many more O2s I need to get rid of because I used them. Two. So I'm going to get rid of that and that. What else do I need to get rid of on my reactant side to kind of balance out what's on my product side? Two carbons. I like it. So done and done. What do I have left to draw? Well, my other product. What's my other product? 4H2O. Okay, so I'm going to draw one H2O. Does everyone agree that's a good model for H2O? Wire N to the chat. Okay. Now, in order to make H2O, what did I have to use? Tell me the atoms or the elements that I had to use to make H2O. Perfect. Have I erased those from my reactant side yet? Or have I removed them from my reactant side yet? Nope. Um, how about now? Am I good from what I've, okay. So now I'm going to draw another H2O. So now I'm up to two H2O. So I'm going to drop this oxygen. I'm going to erase some of this. Then I'm going to get that and that. Am I good from what I needed to draw and what I've drawn? Wire into the chat. Does everyone follow me on this so far? Okay. So now I got to get another one. I'm going to erase. And then I'm going to get one more. Erase the oxygens, erase the hydrogens. Um, does everyone see that you have to, all of the atoms that are reactants, I had to use, right? To make my products. It's not like they spontaneously, oh yeah, this would be fun to make. We had to use the mass and the atoms over here to make these. Does everyone follow that? Add a wire into the chat. Okay. So now I'm going to go back. I'm going to erase all this. And let's go back to that idea of I've got one C3H8, and let's flip it. And let's say that we instead of having one, or sorry, instead of having one C3H8, we have 10. Or sorry, we have sorry, let me rephrase that. We have one C3H8 and we have 10 O2. Um, this is our golden rule. That's what we reference. We have one C3H8 and we have 10 O2. What can you say about the amount of O2 that we have versus the amount that we need to completely consume C3H8? And if you'd like, maybe there are 10 extra O2 molecules. You're very close there. Um, and what I mean by that is, yes, DD8, perfect. We have five extra. So in the interest of time, I'm not going to redraw these, but let's just imagine our C3H8. Actually, I'll draw the O2s. 3, 4, 5, 6, 7, 8, 9, and 10. Does everyone agree that I've drawn 10 O2s? Add a yes or a no to the chat. Okay, so if I reacted one C3H8 with all 10 of these, how many O2s should I erase if I'm making my products? 5. Okay, so if I have 10 O2s and one C3H8, would you agree that I'm going to make 3 CO2s? Yes. And I'm also going to make I'm drawing my products, but now what I'm going to do is I'm going to go back. Do I get rid of the C3H8 in order to make all these products? Yes or no to the chat. Do I erase the C3H8? Y or N? Yeah, I do. Done. Because I had to use those carbons to make my CO2s. I also have to erase 1, 2, 3, 4, and 5 O2s. Because remember, I started with 10 O2s, I only consumed 5 of them. Does everyone follow that? Y or N to the chat? Okay, so would you agree with me that when we started with one C3H8 and 10 O2s, whenever I have that reaction take place, I have more O2 than I need? Y or N to the chat? Perfect. Um, so would you feel comfortable saying that O2 is excess or it's in excess? There's extra that then, or there's extra O2 that you do not need. So this O2 that I have left drawn here, that would be left over. That's still there. So if O2 is excess, we have another term for the C3H8. We say that this is limiting. These are known as excess and limiting reagents. Does everyone follow that? Y or N to the chat? Okay, now we're going to switch it. I'm going to clear all my drawings on this slide. So if you want to get a snapshot of this, go ahead and do so. This is obviously being recorded. 5, 4, 3, 2, 1. Erased. Okay, now we're going to flip this question. When we have 2 moles of propane, or C3H8, tell me how many moles of CO2 are formed. Now, before you answer this question, and I'd like you to answer with a number, what this mentions is it only mentions C3H8. What that means is whenever only one reactant is referenced, that means the other one, there's an infinite amount. So you could rephrase this and say, when 2 moles of propane and infinite O2, how many CO2 are going to form? Answer in the chat based on this. So essentially, the 2 is the only number that you need to worry about to answer this question. Add to the chat the number of molecules of CO2 that are going to be formed. You're absolutely right. It is 6 because this is a ratio. I always like to look at it as 1 to 5 produces a 3 to 4 ratio. When this is kind of like here's the rule and then apply it. Lots of people like to use, okay, here's an example. Lots of people like to use examples or models and recipes. A cheese sandwich. 2 bread, 1 Velveeta slice or Kraft slice. Okay. Does everyone agree that that is the basis for the most simple sandwich that you could possibly make? Okay. Now, what if you have 10 slices of bread and 0 slices of cheese? How many cheese sandwiches are you going to make? Yeah, absolutely. It's 0. Your two reactants in this equation are 2 slices of bread and 1 slice of cheese. You'll make 1 sandwich from that. What if you have 4 slices of bread and 0 slices of cheese? How many sandwiches are you going to make? What if you have 4 slices of cheese and 0 slices of bread? How many sandwiches are you going to make? What if you have 4 slices of bread and 4 slices of cheese? How many sandwiches are you going to make? 2. Because each sandwich has the same makeup. 2 slices of bread, 1 piece of cheese. If you have 4 slices of bread and 4 slices of cheese, you'll use 2 pieces of bread and 1 slice of cheese to make the first sandwich. Then you'll have 2 more slices of bread and you'll get the second slice of cheese to make the second sandwich. Cheese is the excess reagent, bread is the limiting reactant. You're absolutely right. Now, 300 bread using this ratio right here. 300 bread and 300 cheese. How many sandwiches will you make? Add your answer to the chat. 150 sandies. Let's go with 150 slices of bread and 300 slices of cheese. How many sandies will you make? 75. 750 slices of cheese and 12 slices of bread. 6 sandies. Does that make sense? Add to the chat yes or no if that makes sense. Okay. Now, tell me if you want nothing left over, if you want to make 36 sandies, send me a private message, a direct message directly to me. How many slices of cheese and how many slices of bread? In my chat window, I've got this thing that shows up as 2, and then you can adjust it to send it to me, and you can select my name. If you're making 36 sandwiches, okay, think I've given enough time. If you're making 36 sandwiches, you need 36 slices of cheese. Don't worry about it, DDA. It's okay. 36 slices of cheese, and you need 72 slices of bread. Okay. Now, this is stoichiometry. Stoichiometry is a ratio, it's a recipe. Taking a recipe and taking the amounts that you have. I think cooking is a really great application of this. For example, if you found a recipe online that said how to make chocolate chip cookies, it would say a cup of sugar, a cup of flour, or 3 cups of sugar, 2 cups of flour, a tablespoon of vanilla extract, and, you know, 2 cups of chocolate chips. You'd say, okay, cool. What do I have? And you would kind of work backwards based on the recipe. What can you make? So that's what all of this is. That's what stoichiometry is, measuring what you have versus what you want to make. Now you can do the same thing using quantities like masses. So here what we have is when 100 grams of propane are burned, what mass of water is formed? Okay, so we have 100 grams of C3H8. Does this question define the mass of O2? Wire N to the chat. It doesn't. So another way of looking at that, since it's not defined, how much O2 do we have? Infinite. Because this question would be different if it was when 100 grams of propane are burned in 0 grams of O2. That's a different question. But this one, since it doesn't define the amount of O2, you can operate under the idea that the O2 is infinite. Therefore, what is the 100 grams of propane? If O2 is the excess reagent, what is C3H8? I'll give you a hint. It starts with an L. Yeah, the limiter. Perfect. It's the limiting reagent. Now, to answer this question, because this is asking about mass, what we need to do is take our mass of propane, which tell me the mass of propane. I'll give you a hint. It's on the screen twice. 100 grams. We need to take that 100 grams and we need to convert it to moles of propane. Does everyone follow that first step? Okay. Now, once we get it to moles of propane, let me show you something. Our balanced chemical reaction tells us that 1 mole of C3H8 reacts with how many moles of O2 perfectly? Great. 5. So 1 mole C3H8 to 5 moles of O2. If I have exactly 1 mole of C3H8 and exactly 5 moles of O2, how many moles of CO2 am I going to make? Add it to the chat. 3. If I have exactly 1 mole of C3H8 and 5 moles of O2, I'm going to make exactly 3 moles of CO2. Now, if I have, you know, that's kind of what we looked at on the previous page. If I have 1 mole of C3H8 and I don't care about the moles of O2 because it's in excess, would you agree with me that we could look at this and say, well, our moles of propane to our moles of CO2. And therefore, we don't even have to worry about this 5. We could say, well, this is a 1 to 3 relationship. Would you give me that? And do you follow that? No, we're not. Because what we're doing right now is we are looking exclusively at moles. This is kind of like if you have two slices of bread and infinite cheese. Man, oh man, infinite cheese. What a world to live in. Infinite cheese. You'll make one sandwich. Why is that? Well, because bread is your limiting factor. That's your limiting reagent. Does everyone follow that? Okay. Now, we can relate the moles of propane to the moles of CO2, and that's what, or sorry, and then we can also do the same thing with moles of propane to moles of H2O. 1 mole of propane will produce 4 moles of H2O. This question is asking us the mass of water that's formed. Do we even care about these two, or this reactant and this product? We don't. We know that this is an excess, and this is also a product, but we don't really care about it because it's also being produced. The question doesn't ask about it, so we don't care about it. So I'm going to switch that to moles of H2O. Would you agree with me that 1 mole of propane produces 4 moles of H2O in this chemical reaction? When the O2 is in excess, according to this example problem. Okay, great. So what we need to do then is we have our mass of propane. We can connect that to our moles of propane, which we will do that in just a moment. Whenever we are talking about moles of propane, we can relate that to, from our balanced chemical reaction, our moles of H2O. And then when we have our moles of H2O, we can relate that to, well, our mole or our mass of H2O. So what I'm going to do is show you how to do this. And then we're going to look at another example. And just a second, I got to see what's left on the slide there. Yeah. Okay, good. Um, so we'll tackle, yeah, no, we're good on time. Okay, what is our molar mass of C3H8 if carbon is 12 grams per mole and hydrogen is 1 gram per mole? 44. Great. Now my question is, we have 100 grams of propane. Do we have more than 1 mole, less than 1 mole, or exactly 1 mole of propane? We've got 100 grams of it. Yeah, we've got more. Would you agree with me that we've got more than 2 moles of propane? Tell me if I had 2 moles of propane, 88, exactly. Does everyone follow that? Wire into the chat. Just that math, that we'd have 88 grams if we had 2 moles of propane. Okay. We've got 100 grams. What we're going to do is we're going to divide that by 44. That's going to tell us that we have 100 divided by 44. We've got 2.27 moles of propane. Does everyone agree with that? Okay. Um, so would you agree with me that now that we've defined the number of moles of propane, we're right here in our relationships? Okay. Now, for the sake of simpler numbers, let's just call this 2.3 moles propane. DDA, you're right. What's that 9.09? Add to the chat what that is. 2.27 times 4. Now add to the chat with words what it is and not describe, not don't type out 2.27. Instead, what is the 2.27 and what is the 4?
The 2.27 is the molar of a propane.
Yep.
We did from dividing 100 grams to 44. And then since it's a 1 to 4 ratio, we just multiply it by 4 to get the 9.09
9.09 what?
moles
Moles of what?
of H2O.
Perfect. Thank you very much. Well done. Well done. Well done. Well done. So we're talking about 9.09 moles of H2O. Now what we need to do is we need to look at H2O. We need to calculate the molar mass of H2O. And I'll tell you, hydrogen is 1 gram per mole, and oxygen is 16 grams per mole. So tell me in the chat, what is the mass of 1 mole of H2O? Close. Whoop. Roll it back a little bit. You have oxygen, which is 16. Then you have hydrogen, but you got 2 of them. And we do not need to worry about that 4 right now. 18. 18 grams per mole is the mass of H2O. Okay? So now with the 9.09, that's the number of moles of H2O that we'll produce. What is the mass of H2O that we will totally produce? Add it to the chat when you're ready. H2O. You have 9.09 moles of H2O that are produced. 1 mole of H2O is 18 grams. Not quite. If you have 1 mole H2O, that's 18. You have 9 moles, so 1 mole is 18 grams. 2 moles would be 36. 3 moles would be 54. You need to do 9.09 times 18. Sparrow, it looks like your calculator, you missed a digit. Because 9 times 8 is 72. 163.62. That is the total mass of H2O that's produced. So what we did in order to answer this question is I'm going to erase some of this to make it a little bit simpler. Actually, I'm going to erase it all and redo it. To answer this question, what we did was we read it and it said 100 grams of propane are burned. This is propane. 1 mole of propane, sorry, 100 grams of propane are burned. What mass of water is formed? No other reactant is mentioned. It's in excess. No other product is mentioned. We don't care about it. So effectively, this and this we do not care about. All that we care about is this and this. This balanced chemical reaction tells us 1 mole of C3H8 will produce 4 moles of H2O. Done. There's our molar ratio. Can you give me a Y or an N if you follow that? Great. Now, whenever we're speaking the language of chemistry, we need to convert things into moles. 100 grams, is that the same, or 100 grams of propane, is that the same as 100 moles of propane? Y or N to the chat? No, it's not. We have to convert this mass, 100 grams, using the molar mass of C3H8. The molar mass of C3H8 happens to be 44 grams. So we're going to say 100 divided by 44. And that's where we got a 2 I'll call it 2.3 moles of C3H8. Does everyone follow that calculation? Y or N to the chat? Okay. Now what we can do is take this number and we can say, all right, well, 2.3 moles of C3H8, how many moles of H2O will that get us? We know that exactly 1 mole of C3H8 will get us 4 moles of H2O. So we're going to say 2.3 times 4 gives us, in this case, we came up with, DDA did the calculation, 9.09. Let me change this, 2.027. 9.09 moles H2O. Does everyone follow that calculation? Y or N to the chat? Great. Now, when we got 9.09 moles of H2O, is this question asking us specifically about moles of H2 of water that are formed? No. It's asking us for the mass. So we need to use the molar mass of water to figure out the total mass of water that's produced. 1 mole of H2O has a mass of 18 grams of H2O. So we're going to take this and say, all right, well, 9 moles of H2O. If 1 mole is 18 grams, how many grams is 9? And our answer for that was 163 point, it was somewhere in the chat. 27, I don't know exactly. I'll just call it 163 grams of H2O. Can everyone confirm that they understand this last part, 163.62? Thank you. So we went mass to moles. Moles to moles. Moles to mass. Over here, we were talking about propane. And then our mole to mole relationship was relating propane to water. Prop to water. Our mole to mass relationship was looking at water. Can everyone add to the chat if they follow that? Y or N? Okay. Great. So this is not a trivial thing, but there's conversions. These are things that you've done. I want you to do your best to try to relate this to conceptually to something that you've done before. Making cookies, making a sandwich, making an omelet. And I think that that's a helpful way to look at it. So this is effectively what we did. Our mass of our grams to our moles. Okay. Now disregard that. Um, we've already kind of talked about the concept of limiting reactants. This shows us the epic conundrum that everyone experiences when they buy hot dog buns and hot dogs. Well, if you get 8 buns and then you go and you buy hot dogs, you'll get 6 hot dog links, and you'll think, oh, perfect. What do I need to do? Well, this is an operation clearly carried out by the bread making consortium where they say, ha, we're going to collude on this and you're going to have to figure this out. If we look at this and say, okay, well, one bag of buns, bag that has 8 buns, plus links makes hot dogs, HD, there's our chemical reaction. How do we get this to work? Well, in order for this to work, if you bought 2 bags and one thing of links, how many buns would you end up with? This would give you 16 buns. So then what would you have to do to the number of links that you buy? You'd have to get another container of those. So you'd get 2 of those. And now you're at 12 links. What is your excess reagent right here? Buns. Okay. So we continue increasing this. And just a little bit of a spoiler, where we would get is we would get to the point where we would buy, let's see, let's see, 540. Yeah, I think, yeah, it'd be 48, would it? Yep, it would be. You're absolutely right. So we'd buy 6 bags of hot dog buns. That would give us 48 buns. And then we would buy 8 containers of links. So that would get us 48 links. So we'd perfectly be able to make 48 hot dogs. And then, of course, if you did that, you'd have someone who came over and they'd say, oh, well, I'm doing low carb, so I don't need the hot dog buns. And then you'd say, well, thank you so much because I bought 48 of each of these. So now that I have 9 people who are doing low carb and not eating bread, this doesn't help us. Great. Okay. So all of these relationships are important things to understand and, putting together a ratio. Okay. The questions, this and this are the sorts of questions that I want you to be able to answer. These are the questions. This one and this one are the important ones that I want you to be able to answer. And then a follow-up to that is being able to identify a limiting or excess reagent. If you can do that, you're going to be in great shape for these sorts of questions. It's a good way to practice these types of questions. When it comes to moles, this sort of question, use a recipe. Use something that you know. And what I mean by that is something like, um, try to distill it down to something like I use the cheese sandwich as an example. I don't eat cheese sandwiches because it's kind of lame. Um, but that's the concept. You need 2 slices of bread and 1 slice of cheese. Could you make that more complex? DDA, that's a great question. No, not at all. What I would do if I were you is I would try to answer this sort of question because it starts with a product and asks you to work backwards and say, okay, what do I need for this? And then you can pivot and say, okay, well, if I had, you know, it just gives you options to work out in different ways. The limiting reagent is not always mentioned first, so you kind of have to play around with that. And just, like I said, if there's like what you could do is if there's a multivitamin or something that you take every day, you say, okay, well, the container of multivitamins has 120 capsules. If I took one every single day, I would have 120 days. Okay. What if I'm going on vacation and, my plans change in some form or fashion and I'm going to take two for the next week? Well, then what would that mean for every time after a vacation? I don't know. Just that was off the cuff. So those sorts of questions would be really good. Now, preparing a solution. Or does anyone have any additional questions about stoichiometry and limiting and excess reagents? Okay, great. Solutions. We've already talked about like dissolves like. Water is a universal solvent. It is polar. So polar and ionic things love water. And you can make a solution from polar and ionic things very easily. An ionic thing like NaF or NaCl go in there very well. A Those are ionic compounds. A polar substance like, let's go with CH3OH. The presence of that OH makes that a polar substance. That is methanol. Methanol will go into water pretty well. Like dissolves like. Sodium chloride, ionic. Ethanol, polar. Sucrose and other glucose, we'll just go with that. Glucose, C6H12O6. Those go into solution very well. Meanwhile, go into water very well. Meanwhile, something like propane, C3H8. C3H8 is not going to go into water very well because it is non-polar. Now, when you make a solution, will you have concentrated versus a dilute solution? If let's say that you made Kool-Aid. I don't know about you, but whenever I was a kid and I had the opportunity to make Kool-Aid, I always loved that because I'd be like, oh, great. Well, one little Kool-Aid packet goes into 1 liter of water. What about one packet just goes into my mouth or goes into one glass? Well, in that case, is that Kool-Aid going to be super, super strong or is it going to be kind of weak? S for strong, yeah, it's going to be super strong because it is concentrated. Whereas the way that my mom liked to make Kool-Aid, she would take the one packet, add it to 1 liter of water, and then she'd add a little bit of extra water just to get that Kool-Aid to go a little bit farther. And that was always super lame because that was the dilute and less flavorful. Now, concentration is something that we can measure. We can measure a unit known as molarity. That is the moles of a solute going into the liters of a solution. This is the sort of thing, like if I had, just, yeah, okay. Um, if you had, I'm going to give you some information here. Um, 1.2 liters of solution. And let's say that we had 1 mole. No, we'll go with 1.2 moles of solute. And I'll go 1.2 moles of NaCl. Tell me the concentration, the molar concentration, the molarity of this solution based on the number of moles and the volume. Okay. Does everyone follow that? Okay. Now, What about if it was 1 mole of NaCl? What is the molar concentration? Okay. Does everyone follow that? 0.83 molar. You're absolutely right. Now, chemists don't really think about things in terms of moles, though, or in terms of grams. So, whenever you're given something like, let's say, 75 grams of NaCl, that's your table salt, are dissolved in 1.2 liters of solution. What do you have to do in order to figure out the molarity of that solution? DDA, you're absolutely right. So, could anyone add to the chat what is the number of moles of NaCl that we have if we've got 75 grams of NaCl? Which 1 mole of NaCl is 22.9 plus 35.5. So we're going to call that 22.9 plus 35.5 is 58.4. Okay, I like it. So 75 divided by 58.4. Yeah, I like it. 1.284 sounds good. So I'm going to call that 1.28 moles of NaCl. What is the molar concentration of that solution, of that 1.2 liter solution? Done. DDA. Perfect. Does anyone follow that? We got to 1.07 because what we did was, or I'm not going to say we because DDA did it before me. DDA caught the 75 grams of NaCl and divided it by 58.4 grams of NaCl. The 58.4 is our molar mass of NaCl. We needed that. So our 58.4 grams of NaCl is 1 mole of NaCl. This is the number, the 75 is the number I gave you. And I said, hey, we made a solution by getting 75 grams of water and dissolving it in to make a total of 1.2 liters. Does everyone follow the makeup of the solution? Okay. 75 grams of NaCl dissolved in 1 liters of solution isn't really what we're looking for. What we're looking for is how many moles or what's the molarity of that solution. So we did 75 divided by 58. That got us 1.28 moles of our solute. Our solution was a total of 1.2 liters, though. So this is the same, it's our number of moles, 1.28, divided by 1.2, and that's 1.0666667, or we're just going to call it 1.07 molar. Does everyone follow that makeup of that solution? Okay. Now, tell me the concentration of 37.5 grams of NaCl in a 0.6 liter solution, or in 0.6 liters of solution. DDA, you're absolutely right. Because what happened? Well, the mass and therefore the number of moles got cut in half, but then the solution volume also got cut in half. Okay. Now, whenever you're preparing a solution, this is what that process looks like. The first thing that you need to do is you need to weigh out the solid. This, I believe, is a solid known as copper sulfate. Copper sulfate and copper containing compounds. Oh, sorry, it says it on the bottom of the screen. Um, Copper containing compounds are almost always this brilliant blue solution. This is a piece of glassware known as a volumetric flask. It is a very important piece of glassware because it is really good at one thing. On the side of the bottle, it says 100 milliliters at 20 degrees Celsius. Can everyone see this very fine etched line right there next to that green arrow? If you add a solution up to that exact line, it is exactly 100 milliliters. So when you're making a solution, what you do is you take the solid, you add it to this flask, and then you're going to add H2O. Now notice this water is added to about the halfway mark. And whenever that water is added to that halfway mark, you swirl, swirl, swirl to get that solid to go into solution. After that solid has gone into solution, then what you do is you add more water up to this very fine etched line. And that gives you exactly 100 milliliters of that solution. The reason that you do that is because does this solid, does the copper sulfate, does the solid that you use to make the solution, does that take up any space, Y or N in the chat? Does a solid occupy space even when it dissolves? Does it have its own volume? It does. You add water to it and it dissolves, but it still does occupy space. So my point is that if you added the water first and then added the solid, well, then this etched line right here would be a problem. So if you added water and then added the solid, the water or the level of the solution is going to go up. It's kind of like whenever if you're making Kool-Aid and you add the water to the specific level and then you add Kool-Aid, well, that's going to be a little bit more dilute. Okay. Now, that's the process of making a solution. Here, what we see is the process of diluting. And tomorrow, we are going to start class with doing a concentration calculation, a dilution calculation, and then we'll do 1% calculation. So this equation for a solution dilution is M1V1 equals M2V2. You might have heard, or if you took a chemistry class in high school, you might have seen this as C1V1 equals C2V2. So when you compare these two volumetric flasks at the end, do they look the same? They look similar, but one's a little bit darker. Would everyone agree with that? Okay. The reason for that is that this solution, this one that's labeled V2 and M2, is made using a small amount from this solution. So the way that this other solution was made was by taking 10 milliliters. So let's imagine that this is Kool-Aid. If you drank this, Okay, it would have your generic Kool-Aid flavor or the fruit punch flavor. Then let's say that you took 10 milliliters from it and you added it to this other beaker. And to the other beaker, then you added more water to the 100 milliliter marker. Is this solution going to taste the same as this solution? Which one's going to taste better? One or two, if you like the flavor of sweet Kool-Aid. Two is going to taste better. One is going to taste watered down. It's diluted. Does everyone understand that conceptually? Okay. I've thrown enough math at you today. We're going to stop right here. If you understand this conceptually, that's a really good place to be in. We're going to pick up with this tomorrow, doing these same sorts of calculations. We'll also pick up with some of the balancing chemical reactions and stoichiometry calculations at the beginning of class tomorrow. Um, Other than that, though, I hope you have a great day. Make sure that you finish your quiz by 11:59 p.m. tonight. And then we got another one that opens tomorrow at 11 a.m. Other than that, though, if you got any emails, shoot me, or if you got any questions, shoot me an email and I'll do my best to help you out. Thank you guys for coming to class, everyone.